All right, APCalc class, we're going to hopefully finish up this longer set of notes for our solving related rates problems. So the last couple problems, the last three, we have two that are going to involve cone shapes, and then the last one is a shadow problem. All right, so for example 8, it says sand is poured on a beach creating a cone whose radius is always equal to twice the height. So there's a relationship that's important in that first sentence. It says that the radius is always equal to twice the height. So I'm going to write that relationship because we're probably going to, what you find in these cone problems is because the volume of a cone formula involves both a radius and a height, it's good to be able to substitute and have your variables all in terms of either r or h, depending on what we're looking for. All right, so continuing on here, it says if the sand is poured at the rate of 20 cubic inches per second, so there's a rate of change, right? And we're referring to the amount of sand, so that's the volume. So the volume of sand, dV dt, is changing at a rate, and it's growing, so that's a positive 20, okay? And then it says how fast is the height of the conical pile changing at the time when, and then they give us two different heights here. So what is it that we're looking for? We're looking for the rate of change of the height, and so that's dh dt. So that's what we're going to try to find, right? So we've just got this conical pile. It's going to be growing as the sand is being dumped on from the top, okay? All right, so what do we need to know? And they didn't give us this one. Typically, I think they're going to tell you what the volume of the cone formula is. It's 1/3 pi r squared h. So there's our formula for volume of a cone. And like I said, you're almost always going to be able to find a relationship like this, whether either it's going to be stated to you or they're going to give you some measurements and you'll know the radius to height relationship there. And we want to make that substitution before we do the derivative because it's going to make the problem much easier. You know, we won't have to do a product rule or anything like that. Now, because we're looking for dH dt and they give us two different heights here, we want to make the substitution so that we're substituting everything so that it's all in terms of h. So let's replace that r with 2h in this formula and go from there. Okay, so we're going to have v equals 1/3 pi, and then the r we are replacing with 2h and times another h. So as I simplify that, I'm going to have v is equal to 1/3 pi and then 4h cubed. h cubed. We can, let's see, I think we can simplify that maybe a little bit more before we do the derivative here, because we can, let's see here. So if I multiply the 4 and the 1/3 together, we'll call it 4/3 pi h cubed. Okay, so I kind of like the way that looks. That's pretty good. So if I do the derivative of this now, remember that 4/3 pi, all of that is just a constant. So when I do this derivative, we're just doing the power rule. So dv dt on the left side. On the right side, I've got 4 pi, and then I'll have h to the second power. So I've multiplied this 3 down, and that just canceled the 3 in the denominator here, reducing the power on that h to 2, and then we've got dh dt. Okay, so I've got this for my derivative piece, 4 pi h squared dh dt, and now I can put in some numbers here. So we're trying to find how fast is the height changing at the time when the height is 2 inches. So for part A, now I'm going to plug in 2 inches, and we know, they told us the dV dt is 20, so I'm going to put in a 20 for that, and I've got 4 pi, and I'm putting in a 2 for the h. I'm solving for dH dt, and so what's that? It's going to be 16 pi dH dt, and if I divide that out, 20 divided by 16 pi, so I'll have dH dt equals, it would be 20 divided by 16 pi. I can simplify that a little and call it 5 divided by 4 pi, and that's going to be inches per second for that one. Okay, and then for part B, we're just substituting 6 inches, so we still have 20 for the dv dt. We've got 4 pi, and then this time times 6 squared dh dt. So for part B, I'm just plugging in 6 for this h and solving for the dh dt. Okay. All right, so now I'm going to have 36 times 4, which is 144 pi dh dt equals 20. And if I divide that out, 20 over 144 pi, that does reduce. We could divide each by 4, and we would get 5 over 36 pi. And again, inches per second. Okay, so the related rates, the procedure is, it's kind of the same idea every time. You write down what is it that you're given. You're going to have to come up with a geometry formula to relate those variables together and take the derivative and then substitute in your known values, solve for what you need. Okay. All right, example 9. On this one, it's a cone problem. This time it says water is draining from a conical tank, so we'd be visualizing a cone-shaped tank that's probably sitting like this, and then the water's coming out the bottom. And in this one, it states that the rate at which, and so what we're thinking here, this is cubic meters per second, and so that means that the cone, if this is all filled with water, its volume is decreasing, the volume of the water is decreasing at 2 cubic meters per second. So the dv dt, which is the volume of the water, is going to be decreasing. The rate of change is a -2 in cubic meters per second. Okay, it says that the tank is 16 meters high and the top of its radius is 4. So I'm just going to put those in the picture just to get a visual. So this is 4. This isn't really drawn to scale, but that's okay. And then we'd have a 16 for the height. So h is 16 when r is 4. Now, something to note: if you have a cone-shaped solid figure, cross sections in there, if you're looking at these cross sections, you're gonna have right triangles, what I've drawn here, like in that piece, that are gonna be similar throughout the height of this cone. And so what I'm saying here is that the ratio of the height to radius or radius to height is going to remain constant anywhere throughout this cone. And so that when they give you those measurements, what that's allowing you to do is to say, okay, well, I've got a ratio where the radius is always going to be equal to, in this case, 4/16 or 1/4 of the height. Okay, so it's good to write that out because you're typically going to want to make a substitution for that. And as I'm looking ahead, it says how fast is the water level falling, and so the water level is going to be your height. That's going to be, so the rate of change there is going to be a dh dt. That's what we're going to be looking for because it's asking how fast is the water level falling. Okay, and so that's what we need to find. And so I'm gonna give this relationship here as r is equal to 1/4 h, so that I can substitute in for r and have everything in terms of h, since that's the rate of change I'm looking for. Okay. All right, so how fast is the water level falling when, and then we have some heights given to us here for part A and part B, so two different ones again. All right, so let's start again with our v equals 1/3 pi r squared h. And if we do the derivative, well, no, before I do that again, we want to substitute, right? So again, so we don't want to take the derivative and have to apply that product rule. So this relationship, again, they pretty much always are going to give you a height to radius relationship, and you're going to be able to make that substitution before you do the derivative here. So I'm substituting 1/4 h into the formula for r. So 1/4 h squared times another h. And so if I square that, that's 1/16 h cubed times this 1/3. And so that's going to be like 1/48 h cubed. Hopefully you can see that, and then with the pi in there as well. So v equals 1/48 h cubed, and with the pi there. Okay, and so now the derivative shouldn't be too difficult. dv dt, and if I do derivative there, multiply that 3 down, which would be 3/48, and what's that? That'd go like 1/16. So I'd have 1/16 h squared times pi, and I'd have to put my dh dt after that because that was my variable that I'm taking the derivative with. Okay, and so there's our derivative. I think at this point now we can make some substitutions in there for the h and the dh dt, and so they or actually for the dv dt we're solving for dh dt. Okay, so I'm going to put in the -2 here for the dv dt, and the h, that's what they're giving us right here. The water level is the height of 12 for part A, so I'm going to put that in as 12 squared, and then the dh dt, I'm just going to put that first. dh dt is what we're looking for, and then the pi in here, so dh dt. So we're going to solve for dh dt. So 12 squared is 144, and dividing by 16 would give us 9. So -2 equals 9 pi dh dt, and we're dividing by 9 pi to solve, and so my rate of change of the height, the dh dt, would be -2 over 9 pi, and that would be in meters per second. Meters per second, according to the units up here. We got meters, and we got time unit seconds. Okay, so that was for part A, where I used that height of 12 that was given. And now for part B, we can use the same derivative that we had here, but this time we've got a height of 2 that we're substituting. Okay, so we're going to still put in the same dv dt is -2, so I'll have -2 equals 1/16, and then instead of 12 right here, we're going to put a 2, so that's going to be 2 squared pi dh dt, and so 2 squared is 4, divided by 16 we'll have 1/4, so 1/4 pi dh dt, and so if I'm dividing by 1/4, that would be like multiplying by 4, so I'd get like -8 in the numerator, but I'm still dividing by pi, so that would be dh dt would be -8 over pi meters per second. Okay, so those are cone problems. Again, look for that relationship, the radius to height relationship. Make that substitution before you do the derivative. Okay. Okay, last one. This is the shadow problem. These ones can be sometimes a little harder to visualize, I think, but drawing a picture I think is really important for these shadow problems. Okay, so it says, suppose a 6-foot tall person 12 feet away from an 18-foot lamppost. If the person is moving away at a rate of 2 feet per second, at what rate is the length of the shadow changing, and at what rate is the tip of the shadow changing? So we'll discuss the difference between those things. So I'm going to get a light source here, a little tiny sun, or well, I guess that's my lamp, isn't it? So that's a lamp, I guess. Okay, so we're going to do a lamp there, and that's 18 feet tall. And I'm going to draw a person in here. Okay, so this person is 6 feet tall, so that's a height of 6 right in here, and we've got 18 here, and he's walking, it says he's walking away, so he's going this direction, right? All right, so we've got some changing variables here. So I'm going to just call, there's going to be, wherever his shadow ends down here, and from the person, to wherever his shadow ends, that's going to be really the length of the shadow. So when they talk about at what rate is the length of the shadow changing, I'm going to call that length currently x, okay? And then the rate when he's walking, we'll have a dx dt, because that's the rate at which the shadow itself is changing. There's another piece in here I'm going to call, this piece from the person back to the lamppost y. And in part B, when it says at what rate is the tip of the shadow changing, so this is the part that's sometimes a little harder to visualize, but when we talk about at what rate is the length of the shadow changing, well, the person's walking, and his shadow is moving as well, but the distance between the person and the tip of that shadow is what, that's what we're referring to right here. And because the person's moving and that x is changing, that's just the rate at which the length of the shadow is changing, because the shadow is based on the person and where he's standing, and then where the tip of the shadow is moving. But then for part B, at what rate is the tip of the shadow changing? What that really means is in reference to a stationary point. And so, we would use what we then say, what most of the books do here is they'll call this, let's just call this length L, which is, from this stationary light source, and then, this is the rate at which the tip of the shadow is changing. It's like, this thing's just moving in relationship to the stationary light source, not in relationship to the actual person that's creating the shadow, okay? So that's kind of the difference between part A and part B. So hopefully that sort of makes sense. So in other words, so the way I've labeled this for part A, what we're looking for part A is dx dt, and what we're looking for part B is dl dt, okay? So what we want to do is set up some type of an equation here, and so we've got some similar triangles is kind of the way I'm looking at this. I've got this little triangle here that's created by the 6-foot tall guy, that length x, and so there's a little triangle there, and then there's another bigger triangle right here, which is x plus y for one side and then 18 for the other. And so we know that similar triangles are proportional, the sides are proportional. So if I were looking at the ratio of this side x to the person's height, x to 6, that should be the same as the ratio of this horizontal side, which I'm going to call x plus y. I've called it L for part B, but for part A, for right now, I'm just going to go x plus y. So I'm going to say that's x plus y to 18. Okay, so these are equal to each other. And setting this up is going to allow me to make a relationship between some of these variables like x and y. And so the other thing that I should have written down here, where y comes into play, it says that this person is walking away. I drew that arrow, but he's walking away at a rate of 2 feet per second. So what's changing there is the distance from the light post to the person, which is that y. That's what's changing. The y is changing at 2 feet per second. So I'm going to write that down as a information that I'm given. So dy dt, that's growing at 2 feet per second. Okay, and so I need a relationship in here with x and y, and because when I take a derivative, I want the dy dt to be in there. Okay, so to simplify this, I'm going to cross multiply, right? X times 18 and 6 times x plus y. So I'd have 18x equals 6x plus 6y. And if I combine some terms here, subtract the 6x from both sides, I'd have 12x equals 6y. And then if I solve that for x, I would have x equals 1/2 y. All right, now with this equation, which is a relationship between the information, the variables that I was given and the information I plugged in, I can take the derivative of this, which will give me dx dt on the left side, and it'll give me 1/2 dy dt on the right side. Okay, now at this point, what I'm looking for, I'm trying to solve for part A, I'm trying to solve for dx dt. Okay, that's what I'm trying to do for part A. For part B, that's where we'll involve the other piece, but for part A, I want to solve for dx dt. And so now I can plug in the 2 for the dy dt, and then I really should have my value for that. So dx dt is going to equal 1/2 times that 2. So that gives me really 1 for the answer, and it's 1 foot per second is the rate that we're looking at. Okay, so for part A, I've got 1 foot per second. And so again, what I did was I set up a similar, I set up basically a proportion here, just based on the fact I have similar triangles. So x over 6 equals x plus y over 18. Cross multiplied, and then I came up with an expression x equals 1/2 y. Took the derivative of that, which created a dy dt, which I can substitute in for, and the dx dt, the rate of change of the shadow, the length of the shadow. So that was my dx dt. Okay, so now for part B, I'm looking for, like I said, I'm looking for dl dt in part B. Now, L, what we can say for that one, hopefully, okay, since right here, since x is equal to 1/2 y, if that's equal to 1/2 y, and then this piece here is just y, you can probably see that if I want to write an expression for L that's in terms of y, I would have 1/2 y plus y, because x plus y, let me jump over here, so it'd be x plus y, and making a substitution for x, which I had here is 1/2 y, then I can say that L is 3/2 y. Okay, and what I'm looking for again, so what is the rate of the tip, what is the rate of change of the tip of the shadow, or what rate is the tip of the shadow changing? So that's meaning from the stationary light source here, at what rate is the tip of the shadow changing? So that's my L, that's my dl dt. So if I do dl dt, derivative of that, I'm going to get 3/2, and then here's my dy dt. Now the dy dt, again, it's the rate at which the person's walking away from the light source, and that was just that 2. So I'm going to put in a 2 there, and so dl dt is going to equal 3/2 times 2, which should just give me 3 feet per second. Okay, so that's the rate at which the actual tip of the shadow is changing. Okay, not in relationship to the moving person, but just from the stationary light source. Okay, so that is everything for the